These current meters are very common even when we're dealing with something that has nothing to do with current. How do you build now a motor that works? How do you get over this torque reversal? Well, it's not only the torque reversal that is a problem, but there is also the problem that if you could keep this going around, that these two wires would intertwine and they would break. If you rotate it around 100 times, you can see what happens at A and D. It will break. So you have to think of a design whereby you have slipping contacts, we call them brushes. Suppose I have here a conductor which is connected with A, physically soldered to the wire at A. And here I have a conductor which is D. So the loop is where you are. Soldered wires coming out the loop is here. But now the battery, plus side of the battery is here, and the minus side of the battery of here, and this is a slipping contact. In practice, we call them brushes. So that immediately takes care of the problem that the wires wind up. But there's something else which is very clever about this design. If the gap between A and D is an insulator, then what's going to happen when this rotates 180 degrees, A, which now is on the positive side of the battery, this is negative of course, A is now on the positive side of the battery. If you rotate 180 degrees, A will be on the negative side of the battery. So now every rotation, the current will, all by itself, change direction. And we call that a commutator. And so now, what's going to happen is, now the torque reversal will not occur. If at the right moment, the current switches direction, the torque will always want to rotate the loop in exactly the same direction. And that's the idea behind a commutator. The Grade 802 motor contest. You have an envelope. When you open it up, don't do it now. You'll find in there a copper wire, 2 meters insulated copper wire, 2 magnets, 2 paper clips, and some wood. And the idea is that you try to build a motor that runs as fast as possible. For every 100 RPM, an RPM is a rotation per minute. For every 100 RPM, I'll give you 1 credit point with a maximum of 20 credit points. So if your motor runs 2,000 RPM or more, you get 20 credit points. That is equivalent to 2 homework assignments. And these credit points come over and above your course grade. You have my word for that. We'll give you a final course grade, the way that you've seen in the ground rules, in the first handout, and we add your motor contest, what you deserved. For every 100 RPM, you get 1 point plus with a maximum of 20. And we're going to test these motors on the 2nd of April. And I gave you a handout in which I give you some hints, some ideas. There's one idea that I gave you which you may ignore, and that is to overcome the torque reversal. You can build a commutator. That's really not easy. Not only is it not easy, but when you build a commutator, your system may get a lot of friction, and you may lose more than you gain. There is an alternative solution, which I mentioned in my handout that you picked up today, and that is that you design your motor in such a way that when the torque reversal occurs, that there is no current running anymore. And when it is half a rotation further, the torque is there again. The current is there again. So for half the time, you stop the current. You'll see that's very easy. I give you some hints how you do that. So you have to weigh that against the possibility of building a commutator. The bottom line is, the maximum is 20 credit points. That's an equivalent of 2 homework assignments. You get it over and above your course grade. And it's also great fun, believe me. What more do you want? To do physics, get credit, and have fun. That's what I do every day. That's the great thing about physics. We have 5 minutes left. And in those 5 minutes, I'm going to demonstrate to you a motor. What you see there is a current loop. I'll try to make you see it three-dimensionally. This is the current loop. And we're going to run a current in this direction. And we here have a magnet, north-south. Magnetic field is in this direction. And we here have a magnet, north-south. Magnetic field is also in this direction. I'm going to run a current through here. And if the current is in the blackboard, I cross B, I is in, cross B, force is up. This side wants to go up. If this side wants to go up, since the magnetic field is in the same direction here, but the current is 180 degrees in opposite direction, this force will be down. And so there's a torque on this motor. And you will see that. You will see that go like this. However, when it's 180 degrees and it swings hereby, it wants to go back because of the torque reversal. So that's the first thing that I want to show you. And I think I don't need any changes in the light. So here we have this loop, and here we have the two magnets. The magnetic field is by no means uniform, by the way. It's very strong here, and it's very strong there. And now I have to power that. There we go. I can't, yeah, I think I know that this one will come up this side. I'm fairly sure that I have the directions right. Let's first take a look at it. There it goes. So when it's here, notice, it goes up. But now, if I power it here again, it wants to go back. So here, it wants to go up, and here, it wants to go back. So we've got to do something. And that something is a commutator. So if we can somehow reverse the current when it's here, then it wants to go down again. I'll show you that. So now it's here, and I'll drive the current in the other direction. You ready for that? You notice? It now wants to go down. Now it wants to go down. But when it's here, I have to reverse the current. It wants to go up. And if I do that with my hand, I can see whether I can keep this rotating. It may take me a while, but I'll do my best I can. There it goes. Switch, 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 switch. Yeah, got it. Yeah, got it. I'm a commutator. And this motor is going at least 60 RPM. That's 1 credit point for me for this course. Thank you.